Welcome to this course on computational mathematics with Sage Math. This is fourth lecture on linear programming problem, and in this lecture we are going to look at theory of simplex methods. So simplex methods are one of the very important methods to solve any linear programming problem. We will first look at what is idea behind this simplex method. So let us get started. So as usual, this standard linear programming problem is defined like this. It is of minimization type and subjected to equality constraints. All the design variables as well as the right hand side are non-negative. And here omega is set of all x in Rn such that x equal to b and x non-negative. It satisfies all the constraints. So this is omega is set of feasible solutions, and we have already seen that omega is a convex set. And also one of the results says that the extreme points of omega are nothing but basic feasible solutions. So actually the simplex method is about starting with a basic feasible solution, that is starting with a extreme point of omega and moving to another extreme point using some systematic method. So in order to solve this linear programming problem, we actually have to solve this system Ax equal to b, and we know that in case we want to solve this system Ax equal to b, one way to do is employ this RREF, row reduced echelon form, to this augmented matrix AB, and once you employ this RREF, the last column will give you the solution of Ax equal to b. Now in this case we are going to choose solutions only when the right hand side, that is the last column, becomes non-negative. Okay, so let us again recall the assumptions that we made. The rank of A is M, that is A is full rank matrix, and columns of A are written as A1, A2, AN, and we are assuming that the first M columns are linearly independent. Okay. Now what we are going to do, so we will apply RREF to this augmented matrix AB, and when we apply this RREF, since we have assumed that the first M columns are linearly independent, first M columns of this RREF are going to become identity matrix. So this is M cross M identity matrix. The remaining columns, let us write that as ym plus 1, ym plus 2, dot 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 yn, and the last column, which is the column corresponding to this right hand side b, we will denote it by y0. Now if you look at say yk, that is kth column here, where k will be bigger than m, so k can take value m plus 1 to m plus n, and it could be 0. And this column, let us write the components of this column as y1k, y2k, dot 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 ymk. So that is your kth column of this matrix RREF of A augmented with B. This matrix, which we have obtained after applying RREF to augmented matrix, we call this as canonical form of this system, right? So the canonical form of this system is what? The first M columns becomes identity matrix, and the remaining we are denoting it by ym plus 1 to yn, and the last one is y0. Okay, now in this case, let us assume that the last column that is y0 is the last column are all non-negative. In particular, this first M columns are linearly independent and they form a basis. Not only that, these are variables corresponding to basic variables, and which is feasible. So this last column you are getting as basic feasible solution. So all these components are non-negative, right? So so we have got a starting basic feasible solution, And if you look at this, this is going to be one of the corner point of omega. Now, what is that we are going to do? We will move to another corner point in the sense that we need to bring some of this basic variable as non-basic variable and one of the non-basic variable as basic variable. Now, from this canonical augmented matrix, since y0 is a solution, basic feasible solution, so if you, that is same as saying y10 times a1, that is the first column, plus y20 plus into a2 plus dot 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 ym0 times am. This will become the right hand side, that is b, right? That is the meaning of that y naught is a solution, right? So that is what we have. Next, what is that we are going to do? Since we want, first we will check whether the solution, that is basic feasible solution which we have got, is it optimal. In case it is optimal, we don't have to do anything, we stop here itself. Otherwise, we need to update this basic feasible solution, right? That means we need to find another basic feasible solution, and that is same as saying we need to make one of the basic variables from this x1 to xm as non-basic variable and one of the non-basic variable from xm plus 1 to xm as basic variable. In terms of omega, this simply means that we need to move to another extreme point. At present, this basic feasible solution is an extreme point, that is a corner point. So we need to go to another corner point. That is same as saying update this basic feasible solution. Now the question is, how do we do this? How do we find these incoming variables to basic variables and outgoing variables? Okay, so the one variable which we have which is at present non-basic, we have to bring it to basic variable, that we will call as incoming variable, and one which is basic, which we are going to make it as non-basic, we will call that as outgoing variables, right? So how do we do this? Now let us look at, suppose for some reason or using some method you have decided or you have found out that qth variable, that is xq, where q is strictly bigger than m, is going to enter to basic variable. Now if you look at the column corresponding to the qth xq, that is aq. Now aq can be written as linear combination of first m columns and the coefficients are going to come from yq. Therefore, what we have, this aq is going to be y1q times a1 plus y2q times a2 plus dot 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 ymq times am, right? So these are the coefficients of linear combination of aq as a1 to am, which are linearly independent. Okay, so this is true for any column in A, right? Now let us take some epsilon which is positive and multiply this second equation, this is this equation, by epsilon, and then what do we get? So let us bring this aq to the right hand side and write everything on the left hand side and equal to 0. So we have, the equation is epsilon times y1q aq a1 plus y2q times epsilon a2 plus dot 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 epsilon times ymq aq minus epsilon times aq is equal to 0. Now this is the equation you have. We will see little later how we are deciding this epsilon. Now look at this equation, that is last equation, and the equation corresponding to B, which is this equation. Now then let us subtract the second equation, this equation, from the first equation, which is this equation. What do we get? So let us see, when we subtract, the coefficient of a1 will become y10 times y10 minus epsilon times y1q. Coefficient of a2 is y20 minus epsilon times y2q, and so on. Coefficient of am is ym0 minus epsilon times ymq plus epsilon times aq is equal to b. Now, so what we have done, we have written b as linear combination of a1 to am and one extra is AQ. Now what we wanted a basic feasible solution. So the basic variables cannot be more than one. There will be exactly m variables which will be basic variables. At present we have m here and 1 here, that is m plus 1. That means one of them has to become 0, right? Now one of them has to become 0 and also all the coefficients here has to be non-negative, right? Then only you will get basic feasible solution, right? So what we want all these coefficients of a1, a2, am to be non-negative, plus epsilon should also be non-negative. In fact, epsilon has to be positive, then only it will enter into basic variable, but then one of them has to go out, right? That means epsilon has to be equal to some y I0 upon y2 0. Now let us look at in case epsilon is 0, what we get is old solution. Otherwise we have got a new solution, namely let us write this as x dash. The first component is y10 minus epsilon times y1q, second component is y20 minus epsilon times y2q, and so on, and here the epsilon appears at qth place, right? And as I said, in case epsilon is 0, what we get is the old solution, which is y10, y20 dot 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 ym0, right? And in case yiq is negative, right? If yiq is negative, epsilon we have already taken as positive, then this and yi0 is already positive, non-negative. Therefore, each of this term will become positive in case yiq is positive for every q, right? So therefore we don't have to worry about those components. So only thing with that we need to worry is that when yiq is positive, then there is a chance that for epsilon value yi0 minus epsilon times yiq becomes negative. So if this has to be non-negative for everything, that gives me what should be the choice of epsilon, which will make all these components non-negative. And the choice is take the ratio of yi0 upon yiq for only those which are positive, that is yiq is positive, and then define that since this quantity are finitely many, this epsilon will exist, and this will be positive because if all of them are 0, then of course it's possible that all of them are 0, it becomes a degenerate solution, but let us assume that for some this is positive, right? So and to choose the index at which this minimum occurs, let us call that index as p. Okay, so we have obtained index p at which this component, that is namely yp0 minus epsilon times ypq becomes 0. So that will be pushed out of the basic variable. So we have found a index which is going to become non-basic, namely xp, and right, and we have not yet decided what is xq, which is going to be incoming variable. So first we have decided how to find out outgoing variable. Okay, outgoing variable, here in this case we have taken p. Now let us look at how we are going to decide non-basic variable, which non-basic variable will enter, and whether the new solution that we have got, namely this x dash, is this an optimal solution. So the two things that we need to decide: one, how to find a non-basic variable which is going to enter, and second, the new solution that we have obtained, is it an optimal solution? Okay, so now let us look at. Now the value of the objective function at the old solution, old basic feasible solution, which is y10, y20 dot 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 ym0, is going to be z is equal to c1 times y10 plus c2 times y20 plus dot 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 cm times ym0, and let us call this as z0. So z0 is the current basic current value of the objective function with respect to the solution y0, basic feasible solution y0 comma 0 0 0, the remaining n minus m component, right? Now with respect to new solution x dash, what will be the value of the objective function. When we have decided that AQ is going to enter to basic column and AP is going to out of the basic column, and then in this case the new solution is x dash, let us compute what is the value of the objective function for this. So in this case let us compute. So this is going to be C1 times this first component plus C2 times the second component plus dot 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 Cm times this ym0 minus epsilon times ymq plus this is at the qth place, therefore CQ times epsilon. That is the value of the objective function for the new basic feasible solution. Now you can just collect all the components, the first components from each of this bracket, and that becomes C1 y1 0 plus C2 y2 0 plus dot 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 Cm ym 0, but that is nothing but the z0, which is the current optimal current value of the objective function. And the remaining thing that is going to be CQ minus all the coefficients of epsilon, right? So this is going to be CQ minus C1 y1q plus dot 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 Cm yq ymq, the whole thing times epsilon. So let us write this C1 y1q plus dot 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 Cm ymq as zq. Therefore the z is equal to z0 plus CQ minus ZQ times epsilon, right? Where ZQ is what? C1 y1q plus dot 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 Cm ymq. Now if you look at this term ZQ, what is it? If I look at this, the coefficient of objective function, namely C1, C2, Cm and C1, C2, Cn, and let us write the coefficients in terms of these m basic variables, namely C1, C2, Cm, and look at the qth component, qth column of this canonical RREF matrix, then this is nothing but the dot product of CB times YQ, where what is CB? CB is the column matrix of the coefficients C1 to Cm. So that is how we can find ZQ. Now let us look at, in case this, what is our problem was minimization, right? And in Z0 is the current value of the basic feasible solution. And in case epsilon is negative, epsilon is already positive. So if the value of the CQ minus ZQ is negative, the value of the objective function will reduce. That means the current value, which is Z0, is not an optimal value, right? So we need to choose Q such that CQ minus ZQ is negative. And in case CQ minus ZQ is non-negative, this value is not going to decrease. Therefore, what you have got is already an optimal value, right? So that is what we have. So in case CQ minus ZQ is negative, then the value of the objective function is smaller than the old value Z0 or the current value Z0. So therefore, we need to go to the next step, right? And in case they are all non-negative, that is CQ minus ZQ is non-negative with respect to all the non-basic variables m plus 1 to n, then this solution is already optimal, because you cannot further reduce Z0 further, right? So you have to stop this process. Otherwise, now the question is which Q we should choose. In principle, any Q for which CQ minus ZQ is negative, we can select. However, we will select the one which gives me most negative, because you want to reduce the value of the objective function as much as possible. So the maximum reduction will be with respect to the value CQ minus ZQ, which is the most negative. Okay, that is what we are going to do. So now let us just summarize. We have obtained value of Q, that is incoming variable, from the non-basic. And how did we obtain? We have to find CQ minus ZQ for each of this non-basic variable, non-basic column Q, and choose one which is most negative. And then once we have done this, then we find out P, which gives me the smallest of this ratio yi0 upon yiq, and such that yi0 is positive. Now in terms of let us say this augmented matrix, what does it mean? So it means that how we are going to calculate this ratio. So you look at the right hand side, which is your last column, y naught, and look at the ratio of the right hand side upon the incoming column. Incoming column is q, and only those ratio which are for which the coefficient in this column yq is positive, right? So choose the one which is most then you choose the index at which this minimum occurs. That is going to decide what is going to be outgoing variable. We will write this in terms of matrix or in terms of table, which we call as simplex table. It will become very clear. Okay, so that is how we have decided incoming variable and outgoing variable, right? Now this values Cj minus Zj, which we have defined here, these are called relative cost coefficients or reduced cost coefficients. So what is it? The relative cost coefficients, if they are all non-negative, then we have reached the optimal solution. If some of them are negative, then this current solution is not an optimal. You need to go forward. Now let us look at this. So this gives me a result which says that a basic feasible solution is optimal if and only if the corresponding reduced coefficients are all non-negative, right? So at any stage, in case you find all the reduced cost coefficients with respect to this non-basic variables, if they are all non-negative, then you have reached the optimal solution. Okay, that is the meaning here. And of course, the reduced cost coefficient with respect to basic variables are always 0. They are all 0. So only thing we have to worry about the reduced cost coefficients with respect to non-basic variables. Okay, now let us summarize this in terms of simplex algorithm. So that's the what is it? The first step is to convert the given linear programming problem into standard linear programming problem, which we is minimization type, all constraints equality, and all design variables non-negative, right hand side all non-negative. And we saw that what are the steps that we can do in order to convert any linear programming problem into standard form. The next step is to form the initial canonical augmented matrix corresponding to the initial basic feasible solution. Now it is very important. We need to have initial basic feasible solution. Remember we started without loss of generality that first m columns are linearly independent, and those first m columns forms basic feasible columns, and therefore we had initial basic feasible solution. This is the first step. We have to now see how we can guess that initial basic feasible solution. In many cases it may not be easy to guess, so we will see that. Next is you have to calculate the reduced cost coefficient, namely Rj is equal to Cj minus Zj corresponding to non-basic variables. So once we have started with basic feasible solutions, we know what are the basic variables, what are the non-basic variables. So with respect to each of these non-basic variables, calculate the reduced cost coefficient. Okay. Now in case all these reduced cost coefficients with respect to non-basic variables are non-negative, then the current solution is optimal and you can stop. Otherwise, select Q such that RQ, which is equal to CQ minus ZQ, is most negative. In principle, as I said, we can choose any Q for which CQ minus ZQ is negative, but we'll choose one which is most negative. This is actually just a greedy approach, but because we have to ultimately we have to take care of all the reduced cost coefficients which are negative. Okay. But in case all the entries in that incoming column, that is qth column, are negative, are less than equal to 0, then we cannot form the ratio, right? So in that case, this problem is unbounded. This problem is unbounded, because then what happens is that if all these things are negative, we already saw that in that case, you can take any value of epsilon. So the function value will keep on, it will decrease as much as you want. So it is unbounded. Otherwise, in case some of them are positive, then you choose this, find this ratio yp0 upon ypq, for which the ratio is minimum, right? So find that ratio which is minimum, right? And then that p is called, p will be the outgoing in variable, xp will be outgoing variable, and this entry, namely this pq, which we call as pivot entry, and this augmented matrix, look at this pth row and qth column, this you now pivot, that is same as saying make that pqth entry as 1 and remaining all the entries in that particular column as 0, and then again you need to update this. After that you go to step 3, that is calculate all the reduced cost coefficient and all that. Okay, so this is what is called simplex algorithm. Now we will explain this in terms of simplex table. It will become very clear. But so you can see here, the simplex algorithm is all about applying RREF and deciding which is incoming, which is outgoing variable. Okay, so in case you have not understood at some part, don't worry, when we actually take an example and work out these steps, it will become quite clear. Okay, so let me also mention that there are possibilities. We already saw in case of two variables, there are problems in which you have alternate solutions. Many solutions are possible. There are problems in which is unbounded. That also example we saw. So in this simplest algorithm, you can decide when the problem is unbounded. That is, if in once you know what is the incoming variable, but then all the entries in that incoming column are negative, then the problem is unbounded. The second case is you have case of alternate solution. So in simplest algorithm, alternate solutions are detected when there are 0 value reduced cost coefficient for some non-basic variable. So in case some reduced cost coefficient with respect to non-basic variable is 0, then there is a alternate solution. Again we will see that example, so it will become clear. So let me stop here. In the next lecture we will take some problem and we will solve this using simplex algorithm. Thank you very much.